Hello everyone. I'm very sorry that I had to cancel a lecture yesterday. I had a unexpected emergency that happened just as I was on my way out to come down. I'm going to record this lecture for you, but I will also review this material in lab on Wednesday to make sure that everyone's up to speed. So to quickly review what we talked about last class, we started talking about SPI, the Serial Peripheral Interface, which is a synchronous protocol in which two modules communicate with a channel where there is a clock in the channel that synchronizes the flow of information. In this case, this is a master-slave type of channel where the master entity is the one that initiates all communication, and then the slave responds to it. In this case, the master is typically the processor and the slave is some sort of peripheral. The channel is comprised of four signals. There's the clock, which is the clock that's driven by the master, and so the master side is what is determining the data rate of the channel. And then there is two data channels, MOSI and MISO, which are both single bit. The MOSI goes from master to slave, and MISO goes from slave to master. And then there's a slave select that is a active low signal that is used to specify that the channel is in use. We talked about how SPI has different timing modes. So the timing mode is something that the master and slave would have to agree upon before any communication can take place. And the timing mode is comprised of the parameters CPOL, which stands for clock polarity, CFA, which stands for clock phase, and as well as whether the most significant bit or the least significant bit is sent first in the data signals. And so we looked at the four of those. CPOL is the idle state of the clock. So when CPOL is 0, you can see that the clock is 0 when the channel is idle. When CPOL rather is 1, the clock is 1 when the channel is idle. And then CFA is the phase. This one's a bit more complex, but basically it just determines when the data begins changing during a communication relative to the clock. So when CFA is 0, it means the data changes before the clock, and when CFA is 1, it means the data and the clock have their first transition at the same time, which in practice what this means is that when CFA is 0, it means that both sides are sampling data on the first edge of the clock, whereas when CFA is 1, both sides are sampling on the second edge of the clock. So in practice, it's between the two signals. It is telling both sides, or both sides are in agreement in terms of which of the clock edges the data is being sampled on initially. So if CPOL is 0, the first edge of the clock is going to be a rising edge because the clock starts out low. So if CPOL is 0 and CFA is 0, that means that the data is sampled on the first rising edge, whereas if CFA is 1, then the data is going to be sampled on the first falling edge because the clock will start out low, it will go high, and then come back low, and it's going to be the second edge. So you can see, for example, here's in the lower right-hand corner, CPOL is 1, CFA is 1, and so you see that the clock and the data change at the same time, but what the important thing here is not the fact that they change at the same time, but the important thing is when the data is sampled. So because the clock changes with the data, you don't want to sample on the first clock edge because the data is in flux. It's in a state of change at that point. So you want to sample the data on the second rising edge. And so the second rising edge the second rising edge of the clock is 1/2 cycle after the data has changed, so the data should be stabilized. So that's how you figure that out. So in general, just to kind of tie this up, if CFA is 0, you sample on the first edge of the clock, and if CFA is 1, you sample on the second edge of the clock. Now what that edge is depends on CPOL, because CPOL tells you what the clock starts out as. Okay, so we had an example here, which I went through in class, and then we talked about how SPI fundamentally has these exchanges, which are 8 cycles of transfer between the master and slave, in which 8 bits are transferred in both directions. But in order to perform a transaction, which is a more meaningful type of communication, where the master is loading or storing data to an address, you need a transaction which requires multiple exchanges. So the idea is that here's a better example. So if here's an exchange, these are 2 exchanges actually forming one transaction, and the first exchange is the way that the master conveys the address, and then the second exchange is when the data is transmitted, and the data is being driven by the master side on a write and the slave side on a read. And so basically what that means is during a transaction, the utilization of the data lines is only basically half, because in the first exchange, only the MOSI is being used, and in the second exchange, only the MOSI is used on a write and only the MISO is used on a read. The determining whether it's a write or read depends on the protocol you're using, which it can be arbitrary. So in this example, let's see, how are we determining this? So in the first exchange, the least significant 5 bits is the address, and then there's a read-write flag, which is the most significant bit. So in this example, you're going to look at the first bit of the first exchange to determine if it's a read or write, but that depends on the transaction being used. But in general, the load or store information is going to be contained in that first exchange. It's kind of like the header. So we have some examples there. I ran through that. There's also the possibility of having one header exchange and multiple data exchanges if you want to do multiple reads and multiple writes. And so in this example, we have a second flag bit in the first exchange that's going to tell the slave that we're going to do, it's a way for the master to telegraph to the slave that we're doing a multiple byte transaction. And again, this is just the arbitrary protocol that we've defined. So in this case, the first bit of the first byte being sent from master to slave determines whether it's read or write. The second bit is multiple or single, and then the next 6 bits that are remaining in that 8-bit exchange are the address. So in this case, the way we've defined that second bit, the single or multiple bit, is 1 for multiple, 0 for single. And so we've set it to 1, which means multiple. And in this case, we did 2 bytes. In this case, we read 2 bytes, right? Because the first bit indicated that it was a read because the bit was 0, and you can see that the RW, the R has a bar above it, which means that it's 0 means read. Now you might say, well, how do we know that we know the header byte indicates this is a multiple read, but how many bytes are we reading? Well, in this case, this protocol is assuming that as long as we hold down the slave select, the number of cycles we hold down slave select will determine the total length of the transaction. And if we take the length of the transaction in terms of clock cycles and divide it by 8, that will give us the number of exchanges. And then if we subtract 1 from that number, that will be the number of bytes that we read. Now, I talked last lecture about in Lab 1, we have a little different way to handle that, and I'll get to that shortly. So, in fact, I'll talk about that now. So in Lab 1, I discussed this in lab just in case you missed it or if you need a reminder. The lab involves us giving you these signal trace files that have a very simple text format where basically there's samples in the file. The number of samples is the first thing in the file at the top. In this case, there's 12 samples. And then there's a line that has the signal names separated by white space. In this case, we have a trace file that contains a clock signal and then S0 through S7 data signals. In the lab, these will not be S0 through S7. We'll have MOSI, MISO, SS, and S clock. And there's also signals in there for CPOL and CFA as well that are embedded inside the trace file. And then the third line has the widths of each signal. And then subsequent lines are the sample time, and then the corresponding values. I mentioned you don't need to know how to read this necessarily, though, because we give you an API in C and in Python, which allows you to very conveniently read this file. So basically, if you're in C, you can load the waves using the parse file function. You want to use, generally, you want to use standard in. Now, you could use a file pointer here in your code, but the problem is that our grading script assumes that you're reading the data on standard in, so you should use standard in. And then there is a function to find the next edge of the location, the time of the next edge relative to some current time in the file. And then you can also read the signal at a time. So between those two functions, you will have the ability to decode these SPI exchanges and transactions. So in this example, we want your code to say read 111A. So read is the operation, 11 is the address, and 1A is the corresponding data. And then if it's a write, it would be write 3B39. And then if you have a streaming read or a multiple byte read, it would be, for example, read stream, the address, and then the 2 bytes. Now in this case, the streaming protocol is a bit different than what we described earlier. In this case, we have the header byte that's sent by the master has 5-bit address, rather a 6-bit address, a bit for read or write, and a bit for single byte read or write, or streaming, which streaming is just another word for multiple byte read or write. But instead of indicating the length or the number of bytes using the SS signal, we have the master send a second byte out with the stream length that indicates to the slave how many bytes are being read or written. So that may seem a little redundant because, of course, we also have the slave select that's also determining the length of the transaction, but we put that in there just to complicate the protocol just a bit, and of course it adds a little robustness as well. Okay, and then so in part 3 of the lab, as I mentioned, you also have to be able to decode the data with arbitrary CPOL and CFA, which are conveyed to you through the data files. Okay, so that's the lab. If you have any questions, we can address those in lab on Wednesday, or of course feel free to contact us. So one thing I want to go back and mention, one thing I didn't get to last lecture. So with SPI, I've only mentioned cases where you have one master and one slave. There is the ability to have multiple slaves. In fact, it may seem obvious, because if you have a system like an Arduino and you have multiple sensors attached, you may only have one SPI channel, but you want to be able to talk to multiple endpoints on that channel. Like I said, multiple sensors or output devices. So does SPI support that? It does, and there's different ways to do that. One option, and I'll start with this option 2 on the right. One option is use daisy chaining, which is where the slaves are connected in a way where the master initially sends its MOSI out to the MOSI on the first slave, but instead of the MISO on the first slave just going back to the MISO on the master, the MISO is connected to the MOSI on the next slave in line. So you have like basically a chain where data is sent from, so in other words, the first slave acts like the master of the second slave, and the second slave acts like the master of the third slave, and then the third slave acts like the top level sort of slave to the master. The problem with this, though, is that when you use the daisy chained approach, every time you do an exchange, and this is not, this is just every exchange, would have to not be 8 bits anymore. It would actually have to be 24 bits, because you have to move 8 bits all the way through all 3 slaves. So in other words, it acts like a shift register, sort of, where bits are sort of flowing through from the master into the first slave and then the second slave and the third slave. So you have to basically, the number of bits per exchange goes from 8 to, in this case, 8 times the number of slaves. So in every single time you have a transaction, of course, all the endpoints, all the slaves have to participate. And that's an option. Another option is to use this independent approach where the master has multiple slave selects that go to each independent slave. Now, with the daisy chain, the problem with that is that the slaves, of course, have to support this daisy chain, and you may have peripherals that don't support that. In the case of the independent approach, it may appear at first that you could just, as long as the master has multiple slave selects, you could have as many slaves as you want. You know, you have one slave select goes to each slave, and then the MOSI and MISO lines are shared. So the MOSI is kind of fanned out to all the slaves. It's connected to all the slaves, and the MISO, as well as the clock, rather. The clock is fanned out to all the slaves. The MOSI is fanned out to all the slaves. And then the MISO is also shared. But that's the one that's the problem. Because in the case of S-clock and MOSI, only the master is driving that, is only setting that signal. In the case of MISO, all the slaves have to have the ability to set that signal. And that's a problem because if more than one slave attempts to drive that signal at one time, it'll cause problems. It could cause a short circuit, for example, if one of the slaves is trying to set it high, you know, to 1 and the other slave is setting it to 0. So you have this problem, and you might say, well, why would they do that, you know, if they're not selected on their corresponding slave select? And the answer to that is that if it depends on the type of driver. So even if the slaves aren't active, they may still have a driver connected to the pin on their MISO that's always setting it, for example, to 0. In fact, if you go back and look at these examples, the timing diagram examples, you can see that before the transaction begins, or before the exchange, or before the transaction begins, we have this don't care value for the MISO and MOSI, but the MISO, for instance, may still be getting driven by the slave to 1 or 0 before the exchange happens. So the goal is to have it not do that. And so in order to support the independent approach, the slaves would have to support this notion of, sorry, I'm going to skip ahead of here a bit. They would have to support this notion of using tri-stated pins for their MISO. So normally, when you have an output pin, the output pin of a chip is connected to 2 transistors. One transistor is responsible for setting the output pin to 1, and the other one is setting it to 0. And the problem with this kind of arrangement is that one or the other transistor is activated at all times, which means that the pin is always being actively set to 0 or 1. And in that case, you don't want to have 2 chips that are actively setting the same wire to 0 to 0 or 1, or well, what you're trying to avoid is having there be a conflict where one's pulling it to 0 and the other one's pulling it to 1. Now you can avoid this if the chips are equipped with a way to electronically disconnect the chip from the wire. So this is usually called a TriState Buffer. And so a TriState Buffer would be some additional circuitry that would allow the slave to basically not drive its MISO pin when it's not participating in an exchange by basically disengaging and causing its output to be floating, essentially. Not, floating means it's not actively driving. And so some chips will support that. Other ones will always be driving that bus. So the problem here, as I mentioned, is that if you don't have the tri-state bus and you've got one endpoint or one chip that's driving MISO, trying to pull MISO high, and the other one's trying to pull it low, what you end up with is this, basically a low impedance path from the power supply on one chip to ground on the other chip. And in the case of SPI, you're assuming that that these chips all the chips on the channel have a common ground. So the problem is that you can end up with a large amount of current flowing out of one chip and into another chip. And the effect is that it'll put the voltage level of that wire, typically somewhere in the forbidden zone between active, high and low. So if it's a 5-volt system, it might put it in the middle at 2.5 volts. So, one, you have a lot of current flowing there, and 2, you have the signal of the bus would be undefined. So that would be one option for having multiple slaves, but either way you do it, whether you use the daisy chained or the independent method, you have to have special hardware support for that. Normally SPI, at least in my experience, is generally point-to-point. If you want to have multiple slaves, the solution there is normally to use I2C, which we will also talk about in this lecture just a little bit later. But before we get to that, I want to talk about UART. This is another protocol, and this one is notable for being an asynchronous protocol, which means that there is no clock signal embedded in the channel by which the chips synchronize. So UART is a very simple protocol. It just has nominally 3 wires. There is a transmit on one side that connects to the receive on the other side, receive on one side that connects to the transmit on the other side. There's no master-slave. They're basically just both entities or both modules on the channel are peers. And then there's typically UART is shown with a ground wire, although technically, as I mentioned, SPI also has a ground wire. It's just it wasn't shown on the wiring diagrams I showed, but it's assumed that with SPI you have a common ground as well. So UART is also a serial protocol because the both data bits are flowing in either direction are 1 bit. UART, though, is typically sent from the bits are sent from least significant bit to most significant bit. So, when you read a timing diagram, and that's the case, and it usually is with UART, you have to reverse the order of the bits that from left to right. Now, UART, the way UART works is there's no slave select. So the way that a entity that is receiving a UART data wire knows that the other side is initiating communication is through something called a start bit. So the idle state of the data wire is 1, is logic high. And the start bit is when there's 1 bit of data that is 0 that's transmitted through the channel. Now you might say, wait a minute, hold on. If there's no clock signal, then how do you know when to sample the data, and how do you know how long a bit is? Because the bit time, the time that a bit is on the wire, on the channel, depends on the speed of the channel, the data rate of the channel. And normally if you have a synchronous channel, the data rate is determined by the clock signal, whereas with an asynchronous channel, you don't have a clock. So the way this is resolved with UART is that both sides of the channel need to pre-agree on a channel speed called the baud rate. And so the baud rate is the number of bits per second that are sent through the channel, and the reciprocal of that rate is the bit time. Now the problem with that is that you end up having 2 different clocks on either side of the channel, where one is used to generate the data, the other is used to sample the data. And how do you know that when you're sampling the data, you're not sampling the data just as the data is changing? In other words, how do you know the data is stable when you sample it? And the answer is you don't. For that reason, UART channels typically run slower than SPI. They run actually, very slow, usually on the order of kilohertz or kilobits per second. And that's okay because UART is generally used just for textual consoles. So it's not a big deal that it runs slow, but by running it slow, you minimize the chance that you'll have the receiver go into metastability by just happening to sample the data when it's transitioning, although it does happen. And there's a way to deal with that, which we'll talk about here in a moment. So you have a start bit that is 1 bit time of the data wire being active, or logic 0 that indicates the starting time of the transmission. Then you may have 8 bits that are sent across. UART is normally transmits 8 bits at a time through the channel like SPI, and then you have a stop bit which is when the channel is the data channel is high for 1 bit. Okay, so you have a start bit is low for 1 bit time, stop bit is high for 1 bit time. So why is the stop bit 1? Well, the stop bit is 1 because that allows you to separate two bytes that flow across the channel if they're coming in consecutively. Like if you're trying to send data as fast as you can, you guarantee that the stop bit goes high, which is also the idle state of the channel. So that allows you to separate 2 bytes. Now, data does not have to flow, just like with SPI. You may get sporadic, bytes that transit the channel. You're not necessarily going to have consecutive bytes flowing through, but the stop bit being 1 and the start bit being 0 just guarantees that you have a transition, a data transition, a falling edge of the data in between every to bytes that are sent. Okay, so now there's some additional optional features that UART offers. There's something called a parity bit, which is an additional bit you can add after the data that can be used to detect if an error occurs. And as I mentioned, that can happen not only because of channel noise, but it can also happen because of the metastability problem, where the receiver may just read the data at a bad time during a transition. And as I mentioned too, the data rate between the two sides of the channel have to be prearranged. That's called the baud rate. And then that differs from the throughput, because the start bit and the stop bit and the parity bit are bit times. So they take 1 bit time, whereas the data bits are intermixed with the start and the stop bit, which means the start and the stop bit and the parity bit is essentially taking time up in the channel. And so your throughput, which is the rate at which actual data bits are sent through, is reduced relative to the baud rate. So the baud rate is the bit time on the channel, which includes all the overhead factors like start, stop, and parity, whereas the throughput is the baud rate multiplied by the number of data bits, the ratio of data bits to the total number of bits required to send a byte through, which includes the start, stop, parity, and and any other bits that are sent. So, for example, you can have something like this, where you have in this transaction I show, or transfer I should say, I'm showing that this channel is configured for 7 bits, 7 data bits. Now, as I mentioned, it is possible. It's most often the case that you have 8 data bits, but you can have 7 data bits or 9 data bits. The bits are sent least significant bit first, which, as I mentioned, is also standard for UART. There's no parity, and there's 2 stop bits in this case. Now, if you do have more than 1 stop bit, they're both high. So that just separates individual bytes out. So in order to read what's happening here, you have to first ignore the first bit time, which is the start bit, and then we count 7 data bits. So going from transmit to receiver, or being transmitted, I should say, you've got a 0, 0, 0, 0, 0, 0. Okay, so that's 1, 2, 3, 4, 5 zeros, and then a 0, 1, and then your 2 stop bits. And then on the receiving side, coming back the opposite direction, you have the data being sent as 1, 1, 1, 1, 1. So that's 5 1 bits. 1, 2, 3, 4, 5. So I'm sorry, we actually had 6 0 bits on the first line and 5 1 bits on the second line, and then a 0 0. So 1 1 1 1 1 0 0. Right, 5 ones, 2 zeros, and then the 2 stop bits. So that's shown up here. Now the problem is that, remember, it's least significant bit first. So when I read least significant bit first, I have to read the bits from left to right, but then I have to reverse the order when I express those as a value. So least significant to most significant is 0, 0, 0, 0, 0, 0, 1. That's again on the transmit side, but I have to reverse the order of those to show them in most significant to least significant, which is how values are typically represented. So the value actually sent is in hex would be 4 0. Okay, so this is the same data. One other thing I want to point out too is that the transmit and receive are shown here lined up. It's implying that 1 byte is sent for every received byte, and that doesn't have to be the case. This is just shown for convenience while reading these things. Generally, the transmit and the receive side are both independent, and they usually they're not active at the same time. I mean, it's possible, but usually, as I mentioned, it's for terminals. So, you're typing a command on a terminal and then hitting enter, and then you're getting data back. So a lot of times, only one of these are active at any time. So this is showing all the different parts of this. This is the same example we looked at before. We've got the start bit there. We've got the data bits, 7 data bits, and then the 2 stop bits. Now, the parity, I haven't talked about that too much yet. So the parity is a bit that's appended immediately after the data and before the stop bit or stop bits. And this is an error detection bit. And so there's 2 modes that we can use the parity. There's odd parity and even parity. And this part is a bit confusing because you would think that odd parity would mean that that the odd parity would be true if there's an odd number of 1 bits in the data. But as it turns out, that's actually not how it works. That's, believe it or not, it's the opposite of how it works. The odd parity is asserted if there is an even number of 1 bit set in the data, because it guarantees that if you look at the data and the parity together collectively, that there would be an odd number of 1 bits set. And the same thing goes for even. So depending on how I set up if I set up the UART channel with even parity, as opposed to odd parity, then the parity bit time, which is right after the data, would be 1 if there's an odd number of 1 bits in the data. So here's an example of that. So if we look at the transmit side, we can check to see if there's an error. We can detect up to 1 bit error there. So we have 9 data bits, least significant bit first, although that's not relevant for this example, and there's even parity and 1 stop bit. So if we look at the data bits and the parity bit together, there would be 10 total bits. So if we look at 10 bits starting after the start bit, which is the first bit time, we have 1, 0, 1, 1, 0, 1, 1, 0, 0, 1. Okay, so the total number of 1 bits there is 1, 2, 3, 4, 5, 6. Now again, we're not counting the stop bit in there, and we're not counting the start bit. But in the data and the parity bit, there are 6 1 bits, so 6 is an even number. So according to the parity check, there's no error in this channel. Now, of course, there could be 2-bit errors, which would, if we flip 2 bits in the channel, then we wouldn't detect that. We would only detect a problem if there's 1 bit. Now, on the other hand, if we know there's a bit that's unknown or that was corrupted somehow, this is called an erasure as opposed to an error, then we can figure out what that is based on the parity. So again, this is even parity. So on the receiving side, we've got 1, 2, 3, 4, 5 1 bits, and there's even parity. Well, since 5 is an odd number, the answer is that that unknown bit must have been a 1. So that is shown there, and yeah. Okay, so so here's another question for you. Assume a UART channel operates at baud rate 9600 bps, bits per second, and has 7 data bits, 1 parity bit, and 1 stop bit. What is the throughput? Well, if it has 7 data bits, you're only getting 7 bits, but you have to, when you're only getting 7 bits of data, but you have to transmit an additional parity bit and start bit and stop bit. So essentially what that means is that for every 7 data bits, there are 3 additional bits of overhead. So you're getting 7 data bits for 10 total bits. And so that means that the throughput is 70% of the baud rate. So in this case, at 9600 baud, 9600 bits per second of channel speed, we're getting only 70% of that in data rate, which is 6,720 bits per second. Okay, so here's another example for parity. This is 5 data bits, and odd parity, 2 stop bits. We ignore the 2 stop bits, we ignore the first start bit. So how many 1 bits do we set? 1, 2, 3, looks like there's 3 1 bits. So the missing bit must have been a 0, because if it were a 1, we'd have 4, and that would give us even parity, and there shouldn't be. We can look at that receiving side too. We've got 0, 0, 0, 0, 0, 1, and so there's only 1 data bit on the receiving, or actually one bit amongst the data and the parity. Keep in mind, again, there's 2 stop bits that we ignore there. Okay, are there errors in the transaction below? So we have odd parity. Let's see, 5 data bits, so we count 5 data bits and 1 parity bit, so we count 6 bits, counting the number of 1 bits among the 6 bits. There's only 1 bit set on the transmit side, and so that's an odd number. So no errors on transmit. On receive, we have 1, 2, 3, 4. On receive, that's an even number. That indicates that there must be an error on the receive channel. So the received parity is incorrect. Okay, so let's move on to another channel technology. Let's talk about a little bit more about this topic of having multiple slaves on one channel. So another approach, I talked, with regards to SBI, I talked about the fact that you can have multiple devices that drive a single wire as long as you have the ability to cut they have the ability to cut themselves off from sending a signal in that wire, basically electronically disengaging themselves. Another approach is this notion of open drain interfaces. So before I talk about that, let me talk a little bit, revisit this idea of transistors, in case you haven't seen this before. So transistors are electronic, basically act as electronic switches. So they have three terminals. They have a gate, which turns them on or off. And then there's a drain and source, which are the two ends that can be connected or disconnected depending on the gate input. So you can think of the gate as the input, and the drain and the source are kind of the outputs, but in reality, they're just two terminals that are being shorted or not shorted depending on the gate. Now there's two types of transistors. There's NMOS and PMOS, and functionally the difference here is that with NMOS, the transistor turns on and effectively shorts the drain and the source when the gate is logic 1. Whereas with PMOS, it's the same thing, but it's in reverse. And the way you can tell the difference is that you can see logically there's a little bubble here on the gate for PMOS, and that bubble indicates that the gate is active low. So when the gate is 0 or at logic low, or false logically, it's what turns the transistor on. So normally, when you have a driver or logic gate, you would have at least in CMOS logic, you would have every wire would be driven by a complementary arrangement of both types of gates, where one gate is responsible for pulling the output, shorting the output to high, to the VDD, and the other is responsible for pulling it down to ground, right? So in other words, for each individual transistor, I mentioned they don't really have an output. They're just shorting their source and drain terminals together. So when you have two of these transistors connected serially through their sources and drains, or connected on one side, and then the other side you have VDD and ground, this is what essentially gives you an output, because it allows you to turn one or the other of these two transistors on, which will connect the middle part where the two transistors connect. It'll then connect that to through one or the other transistor to its other side, which is either power or ground. And since these are complementary gates, one's an NMOS and one's a PMOS, and the input is connected to both the gates on both, they're mutually exclusive. Only one turns on at a time. So this is how this is called a push-pull style interface, where you can explicitly drive the output, where the output is the joining of the two transistors. You can pull that up to 1 or to 0, right? So another approach is called open drain, which is where you do away with the pull-up transistor, the PMOS. So you just have a transistor that is responsible for taking the output pin and shorting it to ground, right? And then you may say, well, if that's the case, then how does it ever go to logic 1? It accomplishes that through a pull-up resistor. So there's a pull-up resistor somewhere on the wire, and it generally has around a 10 kilo ohm resistance straight up to the power supply, which in this example I've got is 5 volts. So that way, if neither side is trying to actively pull the wire down to ground, then the logic level of the wire will by default be 1. Now there'll be a slight voltage drop through the pull-up resistor. However, the off resistance, when a transistor is off, it doesn't actually disconnect, but you end up having with a very high equivalent resistance of an off transistor. So you've got a 1 mega ohm, so it could be more, it could be 10 mega ohms, but what you end up with is a voltage divider. And so the 1 mega ohm of off resistance of the transistors is so large compared to the 10, say, kilo ohm pull-up resistor that there's usually only maybe 100 millivolt or so drop. So you still are the output. In other words, if both these guys are off, in other words, the gates on both these transistors are off, then that means the voltage on that line will be about 4.9 volts, something like that. Okay. Now you will have a little bit of leakage current there, but it'll be very low. Okay, so What happens when one of the devices turns its pull down transistor on, right? So you start pulling down to ground, you get an on resistance of about 1 ohm, which, again, it's not, you get a little bit of on resistance through that transistor. But basically what you end up there is you get another voltage divider where that 1 ohm is very small compared to the 10 kilo ohm that's pulling up. So you end up with a voltage that's very close to 0 on the output. And in this case, you get a little bit more leakage current because now you're just having to leak through essentially 10 kilo ohms, right? So you're getting, in this case, about half a milliamp or so. So that's one of the downsides of the open drain interface, is that whenever any of the devices on that wire, the shared wire, and the point here is that you're sharing a wire, but for that shared wire, if anyone tries to set that wire from 1 to 0, you're going to end up with some drainage current as a result. I mean, you get that even with push-pull, but to a much less degree. Now, what you might say, what is the advantage then of this? Well, the main advantage is that it's fairly safe, because even if both devices on this shared wire, they both pull down, you really get, you may get about double the leakage current, but it's still being shunted, through this 10 kilo ohm pull-up resistor. So, it's not devastatingly bad if both devices here both try to talk at the same time. Okay, so the open drain style is the style of circuit that's used by this new bus I'm going to talk about, called I2C, which stands for integrated circuit. Now, the reason why open drain is so important for I2C is that I2C only has 2 wires. It is synchronous, so it has a clock. So that clock is called SCL typically. Now, remember with SPI is SCLK is how I refer to it. But S stands for serial, and then you can have CLK, CL. It's basically just one of these wires is the clock, and the other one's the data, and it's usually referred to it as SDA with I2C as opposed to S data. Now, you'll notice that there's no slave select. The reason there's no slave select is because the I2C uses the open drain technique. Basically, instead of having a slave select, we want this to be a multi-master bus where any device could take mastership. So the way that works is that a device will try to take mastership when it wants to, and if it happens to collide with another device that's trying to take mastership, it's not a big deal because it uses the open drain technique. But at the same time, it can detect that collision happening, and then it can wait. One of the devices, of course, has to yield. So there's no slave select. Also, notice that there is only 1 data line as opposed to 2, as there was with UART and SPI, and that's because this is the I2C only allows for 1 device to communicate at a time. However, whenever you're doing a transaction where you're trying to have both master and slave communicate for the purpose of reading or writing data, obviously that data line is going to have to be shared. So both sides will have to talk on it, and so there'll have to be some kind of coordination over who talks at what point. And that's what the I2 bus is really all about. So let's see, I already covered that. So I2C is serial, 1 bit at a time. It is sequential, sequential, which means there's a clock. I'm sorry, synchronous, which means there's a clock. And it is a multi-master, which means you can have multiple devices on the channel, and you can have any device be a master. So an I2C transaction, and with I2C, all the communication in I2C is in transaction. So there's no notion of an exchange and a transaction as there is with SPI. So basically, you have a start bit, as you do with UART. And then, so the master sends a start bit, and then, and basically that's the way that the master gains mastership of the bus is, if you want to communicate, you send a start bit. And then there is a 7-bit address. There is an extension for 10-bit addresses, but we'll just look at the simpler case of the 7-bit address. Then there's a read-write flag. Okay, now here's where things get a little strange. After the read-write flag, the slave is expected to acknowledge, to send an acknowledge back to the master. So I2C also has acknowledgements, which isn't something we hadn't seen before. So this way the master knows if anyone's listening, you know, if there's a slave that's listening on the other side. After the acknowledgement, there's an 8 bits of data. Now the data is either sent by the master or the slave, depending on whether it's a read or write transaction. So this is where the two devices have to coordinate. And then there's an acknowledgement after the data. Now the acknowledgement is sent by the other side. Whichever side wasn't sending the data sends the acknowledgement. And then there is a stop that's always initiated by the master. So how does the start and stop? Well, one thing I want to mention here is I2C has a clock. The clock is always driven by the master, as it is with SPI, although, again, it's a multi-master, so any device on there could take mastership of the bus and then drive the clock. However, the clock is not edge active like it was in SPI. It is level active, is level sensitive. So what that means is that instead of the data being sampled on the rising or falling edge of the clock, the data is sampled whenever the clock is high. So what that means is that the data signal is not supposed to change when the clock is high, unless some special symbol is being transmitted, like the start or stop. So the start bit is sent by the master whenever the clock is high and the data has a falling edge. So the data's idle state is high, which is true because it's as it is with the clock, because this is an open drain, and as I mentioned, you have that pull-up resistor. So the idle state of the wires, both wires, is high. And normally the data, whenever sending data, whenever sending data, you don't change the data when the clock is high, except for the start. So if you have a start bit, is the time you pull the data down when the clock is high. That indicates a start. So that's kind of a special circumstance. Likewise, the stop is when the data has a rising edge when the clock is high. So falling edge, clock is high, falling edge data start. Rising edge when the clock is high is when, falling edge when the clock, having the data fall when the clock is high is the start. Having the data rise when the clock is high is the stop. Okay, so you can see that on both sides of this. And then normally whenever the data changes, you can see that the data is changing before the clock goes high and changes after the clock goes low. So the data generally is changing whenever the clock is low. So you can think of this like a kind of a tit for tat sort of thing, where the master is giving, for example, well, when the master is sending data, it will change its data, then bring its clock up, and then bring its clock down, and then change its data. And the slave will also do the same thing when it's in control. But however, keep in mind that it's a little bit more complex for the slave, because the master is still the one driving the clock, and the slave will have to be sure to make sure that it doesn't change the data whenever the clock is high. Okay, so let's go back here. So there is an address phase. Every transaction contains an address phase. This is very similar to the kind of the header byte that's sent for SPI, where you're conveying the flags and the address, and then there's a data phase. And then the data that's sent is 8 bits. The difference, though, is that the address phase and the data phase are together, they're 9 bits because they include the acknowledgement. So even though 8 bits are conveyed, there is 9 total bits during the address phase and the data phase because of the addition of the acknowledgement. As I said, the master is always in control of the clock. And so here's an example transaction. You can see the start is indicated by the data being driven low while clock is high, and likewise the stop is indicated by the data having a rising edge when the clock is high. And then how do we read this, though? I mean, how do we extract these bits? Well, this is actually a little simpler than it is for SPI, because all you have to do is look at the value of data when the clock is high. So you can see that if we can put the the master sending a 1 1 1 1 0 1 1, and we're going to count 8 of those off. That's the I'm sorry, actually 7 of those. That's the address, and then the 8th bit inside the header phase or the address phase is, in this case, is the read-write indicator, and then there's the acknowledgement. So you can see there's 9 total bits. So the address here, and this is most significant bit first. I2C is typically most significant bit first, so this is similar to SPI in that way. So the address would be 11111011, and this would be a 0 for the read-write flag. That means that we're doing a write. And so if we're doing a write, so first we'll get an acknowledgement from the slave. Now, because we're doing a write, the slave will take control of the data during the acknowledgement bit. So we kind of have this handoff where the master is in control for 8 bits, and then the slave takes control for the acknowledgement. But because this is a write, the master must take control again of the data. So there's this handoff. There's now two handoffs. We handed off control of the data to the slave for the acknowledgement, and because it's a write, the data is data lines going back to the master for the data phase. And then after the data is sent by the master, the slave then takes over again to give its acknowledgement, to acknowledge that it received the data. So the acknowledge is a 0. A positive acknowledgement is when the data is 0 during the acknowledgement bit. And if there's a 1 during the acknowledgement bit, that is a not acknowledged. Now you might say, well, that seems counterintuitive because it's it's basically negative logic, but it makes sense because if the slave didn't exist or was disconnected or died, remember that the default state of the bus on open train is 1, right? So 0 is proof that there's someone out there actually driving the line low. So 0 makes sense for a positive acknowledgement, because if 1 was a positive acknowledgement, then as I mentioned, if the other side wasn't alive, it would be misinterpreted as a positive acknowledgement. Okay, so here's a couple questions about I2C. What's the stop condition of I2C? Stop condition. Okay, so how do we figure this out? Well, first of all, the stop condition is when we're changing the data when the clock is 1, right? So now, in fact, both start and stop is changing the data when the clock is 1. So the question is, what indicates the stop? It's either the rising edge of SDA when SCL is 1, or actually that's the only option, right? Because we're looking for something changing on the data when the clock is 1, right? And so I think that's the only option, right? So it's A, yeah. So another thing here that, as I mentioned, is this notion of having to constantly sort of switch off on this data line. So the question is, who's in control of the data? It depends on what phase you're inside of the transaction and what type of transaction it is. So again, the SCL is the master is in control. The data, if it's a read, the first 8 bits are always the master. Actually, read and write, the first 8 bits are always the master, and then bit 9 is the slave. But if it's a read, the slave would retain control of the data after the acknowledgement of the address. And so from bits 9 to 17, it would be the slave, and then bit 18 would be the master to acknowledge the data coming back from the slave. And again, it's because it's a read, right? So you send the address and the flags of the slave acknowledges, and then before passing control back to the master, it sends the data that was requested, and then the master has to take control and acknowledge that data. Whereas in a write, the master sends the first 8 bits, the slave acknowledges, the master wrestles control once again for the data to send, and the slave gets control back for the acknowledgement. So there's more changes in control of I2C in a write than there is for a read, because the reason is because of the acknowledgement after the address has to be giving control to the slave just for 1 bit. Okay, so that's all I'll cover today. I don't want to keep you too long with this online lecture. Again, I'm sorry about lecture being canceled today. I will review all this material. I went through it fast, and I'm not sure how many of you will be able to watch this online. So I'll go through this again on lab on Wednesday just to make sure everyone's clear on this stuff. And hopefully we'll be able to finish up the interfacing chapter next Monday. So thank you very much. We'll see you then.